All right, everyone. So today we're going to be talking about the last kind of advanced method of integration that we're going to discuss in this course. And really, we're only looking at a very specific couple of cases of this. It turns out that there's a lot of different ways we can solve improper integrals, and we're only really going to be focusing on one type of improper integral simply because that's just the one that I always see on the AP exams. I don't really see any of the other types of improper integrals, but we'll talk about them nonetheless. So first of all, you might be saying, okay, well, what makes an integral improper? And the simple answer is it's just rude, okay? It doesn't know what to do in certain social situations. An improper integral is like what's a good analogy? Okay, you got a friend that's having a really classy dinner party. Okay, everyone's showing up dressed to the nines. Everything is nice. But for hors d'oeuvres, they're serving cheese and crackers, but the cheese is like individually wrapped Kraft singles when it is clearly brie time, if you know what I'm talking about. All right. If you don't know what I'm talking about, that's good because, yeah, that's not the definition of improper integrals. Okay, an improper integral is an integral of which we're talking about a potentially infinite area under the curve. So a great example of that is if we look at the function 1 over x and just look at from where x is greater than 0. If we want to take the antiderivative, or if we want to evaluate a definite integral, like let's say from 0 to 5 or something like that, it turns out that we run into a bit of a kind of logical problem because when we're around just to the right of x equals 0, isn't it true that we have infinite area under this curve? Okay, the line never ends up, it just shoots off to infinity. So how can we possibly evaluate a definite integral when that's one of the limits of integration? Okay, one of the other problems is, let's say instead of going from x equals 0 to x equals 5, if instead we went from that to infinity. Well, if we go off to infinity, it's also true that we're adding up infinite area under the curve. Okay, so what improper integrals attempt to do is they look at this infinite area in either one of these cases and say, okay, is this infinite area actually infinite, or does it eventually end up settling on some number that we can quantify? And so that's the whole point of it. And this is also kind of an introduction into something we talk about in infinite series, which is convergence or divergence, and I'll explain that on the next slide. And it turns out there's actually a lot more cases when improper integrals come into play. For example, we could have something like the function 1 over x minus 1, which looks something like this. And so, because we have that vertical asymptote at x equals 1, if we tried to evaluate a definite integral across that vertical asymptote, we would come up with a problem because we would have cases where we'd have infinite area under the curve on either to the right or the left of that section. So that's another case when improper integrals comes in. But it turns out, like I said, it would be great if we had the time to go over all the different cases of improper integrals. But to be a little bit more efficient with our time, I'm only going to go over the types of improper integrals that I have seen on the AP test, and that's ones like this, where we have an infinity as one of the limits of integration, or a problem that's something like this, except that would be a 1 and not an infinity. All right. So it turns out the solution to improper integrals is very straightforward. Basically, if we have, for example, an upper limit of integration that's going to infinity, what we do is we replace that with a letter, let's say B. It could be smiley face, it could be whatever you want it to be. But we put a limit in front of that integral and then plug in that variable for the upper limit of integration. We go through and evaluate the definite integral, no different than we would before. But when we get to that last step, we take the limit as that variable B, in this case, goes to infinity. And if that limit is finite, meaning it settles on a number, we call that a convergent improper integral. And if that limit is infinite, it means that there truly is infinite area under that curve, and there's no way we can quantify that with one single number. Okay? So in this example down here, it's just the reverse. This is if we had a lower limit of integration that went to negative infinity. All right? And so again, going over these terms, because these terms are going to be important, if that limit exists when we evaluate the improper integral, that means that the area under the curve in that domain is finite, and we say that that integral converges, meaning the area eventually settles on some number. Now again, some of you might be saying, well, how can something that's going out to infinity eventually settle on a number? Well, the answer is, while it might go out to infinity, all the contributions of area we get as it goes out to infinity might be so insignificant that basically they're never going to change the number once we go to a certain point. And so therefore it actually does end up settling on something. And again, if the integral doesn't converge, if the area under the curve is in fact infinite over that domain, then we say it diverges, meaning that area grows without bound. So let's look at a couple simple examples of evaluating improper integrals. So if you need to go back to the last slide and write down the rule of how we evaluate an improper integral, go ahead and do so. And after you've done that, pause the video and give this one a shot. All right, so if you do this one, obviously we see that we have an upper limit of integration that's infinite. So we can rewrite this as the limit as the variable b goes to infinity of the integral from 1 to b of 1 over x squared dx. So if you didn't get to this step, if you didn't understand how to apply this, pause the video and try to solve it from here on out. Okay, so if you do that, this is just going to be the limit as b goes to infinity. Remember that 1 over x squared is the same as x to the negative 2. So we can just apply the power rule on this thing, and this will end up being negative x to the negative 1 from 1 to b. So if we continue to evaluate that limit, that will be the limit as b goes to infinity of, I'll pull that negative sign out front, this will be 1 over b. Remember, x to the negative 1 is the same as 1 over x, so that's why I'm saying 1 over b right here. Then we have minus 1 over 1. And so if we see this, when we plug in our limit b equals infinity, well, what happens when we put infinity in that denominator? Well, that goes to 0, because 1 over something that's infinitely large is going to be 0. So the answer we're left with, in this case, the negative cancels each other out. We're just left with 1. So therefore, this integral converges, and it converges to that value. So that's kind of an interesting to think about, that if we take the area under the curve of 1 over x squared from 1 out to infinity, the area ends up just being 1. That's kind of one of those things that like keeps you up at night. But we've proved it with the math, so we're all good. Okay? So let's try another one. This one looks very simple, or very simple. Well, it is very simple, but it's also very similar looking to the last one, but you get a very different result. So try to solve this one on your own. Pause the video. All right, so again, since we have a limit of integration that's going to infinity, we will say this is the limit as b goes to infinity. Remember, we say that because the upper limit of integration is going to infinity. The area from 1 to b of 1 over x dx. And hopefully you'll remember that the antiderivative of 1 over x is natural log. So this will be the limit as b goes to infinity of the natural log of x from 1 to b. Truthfully, I should put an absolute value around that x, but I don't, because none of my limits of integration are negative, so I don't have to worry about that. But if I keep going forward with this, this will just be the limit as b goes to infinity of the natural log of b minus the natural log of 1. The natural log of 1 is just 0, and the natural log of b, the natural log function is one that does grow without bounds. So if b goes to infinity, the natural log of b will go to infinity. So therefore, this integral actually goes to infinity. There is infinite area under that curve, and therefore this one diverges. Okay? And the reason I showed you these two integrals to begin with is because this is one of the most common types of questions you get on an AP exam related to improper integrals. And it's if you have something called a P integral. Now, when we talk about infinite series, this is called a P series, and it looks like this. It turns out the rules for them are no different, okay? An infinite P series and an improper P integral are going to have the same type of convergence conditions. And those conditions, and we kind of saw this, but we didn't prove it in the last slide, but it turns out that if that value P, if that power above x is greater than 1, it converges. And if that value of P is less than or equal to 1, it diverges, all right? So if you get a problem that looks like one of these improper integrals with those P integrals in here, you shouldn't be intimidated by a question like this at all. In fact, you're going to be on a gravy train with biscuit wheels, because these are some of the easiest problems to solve on the AP exam. But I think so many students are intimidated just by that infinity up there that they don't recognize that that's just a p integral or a p series if you're looking at infinite series. But anyway, so that's a really nice trick, and it's one to kind of keep in your back pocket for when you're on the exam, because you could get kind of, these are just softball questions basically if you understand this rule. So that could be very good for you. All right. So let's practice one more integral, and in this one we're going to look at the integral from 1 to infinity of x e to the negative x squared dx. So this one's going to be a little bit more involved, but try this one out. Try it on your own. Pause the video. Okay, if you've done this integral, hopefully you'll first realize, okay, well, because we got that infinity in the upper limit of integration, this will actually be the limit as our variable b goes to infinity of the integral 1 to b x e to the negative x squared dx. So hopefully the next thing you'll see is you'll be like, okay, well, we have this relationship between like a function and something like its derivative down here. This is a u substitution problem, all right? If you didn't recognize that this was a u substitution problem, pause the video and try to solve it as one. All right, so if we do the u substitution, I would say set u is negative x squared. If we do this, we also want to make sure that, again, I like to do this, you don't have to do this, but if I'm changing everything to u's, I like to change my limits of integration to u's as well. However, some people might like to do the method where you solve the integral, replace the u's with x's, and then plug in the original limits of integration into the function. They end up giving you the same answer as long as you do it right. So really, it's kind of just what your preference is, okay? But in this case, I'm going to evaluate u of 1, which will be negative 1, and u of b will be negative b squared. Again, I'm plugging in 1 and b just into this function right here. So we got those limits of integration. Now we have to find du. Well, du will be negative 2x dx, so we can say that negative 1/2 du is x dx, and that puts a big smile on our face because we have an x dx right here. So if we go ahead and replace this limit, we'll get this is the limit as b goes to infinity of now the integral negative 1 to negative b squared negative 1/2 e to the u du. And that's a nice little simple integral to solve. That's not that bad, right? So if we solve this, we'll get the limit as b goes to infinity and the integral of negative 1/2 e to the u du is just going to be negative 1/2 e to the u du. Or negative 1/2 e to the u, sorry, no du. But this will be from negative 1 to negative b squared. So now all we got to do is evaluate this limit. And if we do that, let me get a little bit more room here. We will have this is the limit as b goes to infinity of, I'm going to pull the negative 1/2 out of there, and this will be e to the negative b squared minus e to the negative 1, which will just be the limit as b goes to infinity of negative 1/2 1 over e to the b squared minus 1 over e. Okay? So if we go ahead and plug in b is equal to infinity, well, 1 over e to the infinity squared, the e to the infinity squared is infinity, and 1 over infinity goes to 0. So this whole term just goes to 0. So all we are left with is 1 over 2e, a finite area, and therefore there's an n before the v in convergent, and that just looks like a weird hieroglyphic symbol, but you understand what I mean. It's convergent, okay? And so we got that. So hopefully these examples have been helpful to you, and so come to class tomorrow ready with questions if you have any on improper integrals.